Hi, I am Suzanne Chess, co-founder and managing director of Tiabzu. I lead a team of professionals whose life trajectories led them to join in this endeavor. Tiabzu is an energy transition company that provides the tools, techniques, and methods that will make subsea desalination competitive. The following is an edit from a presentation on subsea desalination that opened the Royce Annual Workshop at University of Houston. It provides an introduction to the vision behind and an overview of the Tiabzu systems, methods, and just a glimpse into how we will succeed.
Hello, this is Bob Evans, co-founder and system architect for Tiabzu. I spent countless hours daydreaming on Platform Hilda, visions for the future for these structures. As a platform diving pioneer, D.I. Bolding from Exxon USA invited us to establish an ocean observatory beneath this newly installed platform Hondo, the deepest platform of its time, 850 feet. Watching a reef form or time lapse, we could add up the benefits of this valuable resource. In 1983, with a Kennedy Celsius matching grant from NOAA, my team, the Mussel Company, successfully harvested and canned mussels, demonstrating the commercial viability of repurposing offshore infrastructure for aquaculture. Atlantic Richfield funded Man-Made Oasis, a multimedia presentation showcased at the Cabrillo Marine Aquarium in Los Angeles for decades. It introduced the world to offshore platforms as artificial reefs, sparking new perspectives on their ecological benefits and alternative uses. In 2015, Santa Barbara was in the midst of a severe drought. I was reading about the restart of the local community desal plant. I understood the process and its history. I wondered, why not operate subsea and use the natural pressure of the ocean for desalination? This would reduce energy demands and the environmental impact.
As much as 40% of the energy costs for desalination is not only for reverse osmosis, but also to power the high-pressure, high-flow pumps that move as much as 5 times the amount of seawater as fresh water through intake and pretreatment. Pre-osmotic filtering removes marine life and coastal particulate matter from the seawater. The residual brine concentrate is not only saline-rich, but also includes the remains of this biomass. This biochemical cocktail is discharged back into sensitive coastal waters. Phytoplankton is among the marine life entrained by intake and impacted by brine discharge. Phytoplankton concentrates along coastal zones. It is the base of the aquatic food chain and a primary source of more than half of the oxygen on the planet, releasing more O2 than all plants on land combined. Phytoplankton also absorbs CO2, which is delivered to the deep ocean depths when the life that feeds upon the carbon-rich phytoplankton descends. This is part of Deal vertical migration, a natural carbon sequestration that cycles from surface to a depth of 900 feet every 24 hours. DVM is a planetary climate regulating process that can be adversely impacted by nearshore seawater intake and discharge. Operating subsea, high-pressure, high-flow pumps required only for delivery of purified water from depth to surface or shore. Pumping only the product, the purified water, and not the product source, the seawater, lowers overall energy requirements by as much as 40%. Contributing to energy savings is removing multi-pump pre-osmosis by operating below the ocean's most biologically productive zone. Contemplated depths avoids the impact of desalination on phytoplankton, the marine carbon cycle, and potential negative feedback on climate perturbation that these systems can cause. And no one wants one of these obstructing the ocean view from their Malibu estate. Approximately 50% of the implementation costs for the Carlsbad, California facility is attributed to the regulatory process and mitigation efforts. NIMBY delays implementation for years and chalks up hundreds of millions in front-end costs. The assumption is that the removal of the environmental impacts from intake and discharge, as well as competition with high-value coastal real estate, will lower that price tag. We pulled in our favorite engineer, Ryan Elliott. We hired a team of process, structural, mechanical, chemical, and reverse osmosis engineers at IDI in Knoxville, Tennessee, to design the Tiabzu system.
Hi, I'm Ryan Elliott, mechanical ocean engineer, diver, and licensed professional engineer. I began working with Bob and Suzanne on various projects while in commercial dive school and continued while studying mechanical engineering at Cal Poly San Luis Obispo. Our collaborations continued after graduation while I worked for other companies on various ocean engineering projects, including subsea power infrastructure, ocean observatories, and subsea sensors for the United States, the United Nations Nuclear Test Ban Treaty Organization, and other customers. I also participated in the installation of these projects as a diver, deckhand, or equipment operator, in addition to the engineering, testing, and equipment assembly phases, giving valuable field experience to incorporate into subsequent designs. When we began looking into deepwater desalination, we learned that the primary challenges do not lie with the desalination process. Hydrostatic power-driven reverse osmosis is disclosed in patents issued to Lopez Ferdinand in 1980. Subsea desalination was piloted in the late 1990s by a team of researchers in Italy led by Paolo Pacenti with the European Commission. More recently, a team in China led by Huifeng Cui from Hainan University piloted a turbine-based energy recovery scheme for a reverse osmosis system designed to operate at 1,100 meters and provide fresh water to China's proposed deep-sea space station. GE Water and Power Technologies, now Suez, Siemens, and IDE investigated subsea desalination using methods of DXV water technologies. Efforts were abandoned when confronted with the economics of subsea implementation and operation, such as the cost of specialized vessels and cranes for installation required for their approach, equipment recovery for maintenance and removal, regulatory costs, and how to deal with silt and biofouling. Tiabzu addresses these challenges with its unique approach to deployment and recovery from depth to surface for maintenance or at end of life, and a patented system for buoyancy control. While Tiabzu can deploy using an A-frame or deck crane, it can also launch from commonly accessible harbor facilities and be towed to the installation location. Reducing the size of the handling vessel promises to shorten the time for implementation and avoid costly scheduling delays for heavy lift vessels and cranes with their limited availability and high demand. Not to mention removing their high cost, estimated to start at $200,000 per day, from capital expense budgets. Tiabzu brings the tools, technology, and methods to change the environment for desalination. We leverage natural processes, deep ocean hydrostatic pressure for reverse osmosis, relative density between freshwater and seawater for buoyancy control, and symbiosis with existing offshore infrastructure to make subsea desalination competitive. Planned operational depths for the Tiabzu system are between 410 and 610 meters for water pressure-driven RO, below the ocean's most biologically productive zones. This reduces the requirement for pretreatment. High-volume flow-through limits concentration of extracted salts and suspended solids. Energy savings is a result of only pumping generated fresh water to RO pressure versus conventional systems requiring pumping 5 times the generated freshwater volume up to RO pressure. Operations shallower than 410 meters require additional pre-osmotic pumping similar to conventional systems. This buoyancy system integration is used to facilitate deployment, recovery for maintenance or at end of life, or to position and maintain it at operational depth during mobile operations. For scaled water harvesting fields, the module keel will mate with subsea infrastructure. The Tiabzu system includes an integrated buoyancy control system analogous to a hot air balloon, using difference in density between hot internal air and cool external air for its lift. Its balloon, or bladder, provides lift using the approximate 3% difference in relative density between the RO water and seawater. RO water buoyancy allows safe vertical movement of subsea objects without change in lifting force with depth associated with gas-based methods where buoyant force varies with changes in pressure.
Hi, this is Mike Edwards. My oil and gas career spanned 4 decades, beginning as a field landman before various promotions where I worked in acquisitions, legal, government relations, community and public relations, and finally in investor relations. Besides many years living and working in Santa Barbara, I spent a considerable time on boats in the channel going to and from platforms. I was also very fortunate to join the UCSB Marine Research Team, in a two-person mini sub and saw the abundant sea life on and at the bottom of Platform Gale in 740 feet of water. Approach the repurposing of offshore infrastructure as a collaborative process, working together with owner-operators, leveraging their assets, and having a positive impact on their bottom line. The Tiabzu system is designed to operate independently without any interference with platform operations. The system is cross-supportive with power supplied from the platform and fresh water supplied to owner-operators. This symbiotic relationship establishes a framework for development and regulation for long-term uses. This alternative use for the offshore infrastructure provides a transition as conventional productivity declines. And in the case of Tiabzu, as alternative energy sources come online, the possibility of keeping the assets productive for a longer period. This transformation can create a new and sustainable offshore economy. Our financial models predict a doubling of profits within 5 years of approvals to scale up operations. Subsea Desalination produces high returns despite a low commodity price, less than 42 cents a barrel, as compared to oil at $70 per barrel or natural gas at $40 per barrel of oil equivalent. That price difference is offset by higher production volume of a non-depletable resource, plenty of seawater, coupled with lower energy costs and the efficient design of the Tiabzu system for low capex and its ongoing effect on the LCOW. Co-development provides the framework for regulatory or independent operations before momentum for decommissioning takes over. The alternative use provides a non-depletable assets for transitions as oil and gas productivity depletes and as other energy sources, wind, solar, hydrogen, wave, come online.
I'm Dr. Andrea Neal. I'm the president and founder of Blue Capital. I met Bob and Suzanne back in the day when I was working with Jean-Michel Cousteau and working heavily as a scientific diver. Over the last 20 years, I've led major expeditions across the Atlantic and the Pacific and throughout the Sargasso Sea, as well as accomplished many feats in the waste energy industry, including large-scale industrial production of waste energy facilities. Today, we're going to go through some of the things about Tiabzu, objectives, pilot scale, and replication of the project. The plan is to deploy a commercial scale system next to a platform and conduct a pilot for a minimum of 6 months to confirm predicted operational efficiencies, energy, environmental, and economic outcomes to de-risk the project for financing and performance insurance. This de-risking step allows for easier project finance capacity for industrial, commercial, and government clients to include the Tiabzu system and water supply portfolios. The first stage of the pilot will be to saddle a remote operating vehicle with the small-scale desalination system. The ROV will carry the system to its operational depth and run through the paces to demonstrate system efficacy, operational hours for insurability, and using the generated freshwater as a form of buoyancy for recovering and positioning the module. Successful phase 1 testing and analysis will raise the technical readiness of this system for commercialization of mobile operations and subsea lifting, such as salvage, defense recovery, and heavy lift operations. Co-locating with existing infrastructure will lessen time for planning to production at a much lower capital expense. Shallow locations such as Gulf of America can be accessed with additional pre-osmotic pumping.
The outcome of the 2-hour deep dive discussion on subsea desalination were offers for corporate collaboration with multiple offshore service providers, with the University of Houston joining in. We invite your participation as well by contributing to funding our pilot. More information is available by contacting me, Suzanne at chess7s.com, as noted on this slide, or by contact page submission at tiabzu.com. Now, on behalf of the Tiabzu team, I thank you.